kind of the physical degrees of freedom, just themselves, or you can adopt a procedure where you first just quantize the system as if it were a physical system, and then somehow quantum reduce that. And of course, it depends on many ingredients, what you mean by the quantization, and what you mean by the quantum reduction. You certainly have freedom there, but it raised the question of whether these two things necessarily should be equivalent. And well, certainly with given inputs of what one means exactly by quantization and reduction, quantum reduction, one can certainly find examples where this is a non-commutative diagram. And actually, that's something I looked at in my PhD thesis many, many, many years ago. So my very first paper, I'm proud of it, and now I'm citing it for you, was exactly about this issue of, can you actually find an explicit example that is so simple that you can do both the quantization and of the constraint system and of the unconstrained system without it being totally trivial. So that's a nice. So I give you this as a reference if you want to look it up. But it comes up all over the place, and this was even before the days of the archive. So that's why it doesn't have an archive number. Okay, now I told you also that the procedure of first constraining and then quantizing tends to meet a lot of difficulties in practice, because the reduced space often is not a linear space. And then you are typically confronted with the problem of what on earth is the quantum theory of this system. And anyway, there are no general quantization prescriptions. So that was the arrow, this arrow, right, in my diagram of yesterday. So this is certainly problematic. Typically this is a kind of the configuration space, the physical configuration space, or the associated phase space. Well, just usually the cotangent bundle over this are nonlinear. And that happens even in finite dimensional examples all over the place. So it just means it's not an Rn. And then also this kind of Schrödinger, you don't have global coordinates, and the Schrödinger quantization doesn't really apply, strictly speaking. What it means for the field theoretic case is that you often end up with constraints on your field, so that not all of your field components, take values on the entire real axis or in the complex numbers, but you have, for example, inequalities. And an example of that, of the inequalities, we had, for instance, already seen before reducing for the space of a matrix in general relativity. Right? You had a determinant condition, and of course that really means also that that space is not, strictly speaking, a linear space, a space of all metrics. So that makes it usually really difficult to follow this path. Of course, there are some exceptions. So what you generally do is the other thing. So you first, you start by quantizing, and then you constrain. And then the procedure you usually adopt for reducing the system to its physical degrees of freedom in the quantum domain is what goes by this name of Dirac quantization. And what it means is you take the classical constraints, the constraint functions on phase space, you try to map them to well-defined operators, and you then look at a subspace of all Hilbert space that is where, which is annihilated by these constraints. So this was then described as a Dirac quantization. So this is typically the procedure that is adopted. Now, an example I had written briefly down on the board yesterday, but let me spell it out in a little more detail to see how this makes sense. So suppose S, my finite dimensional phase space, is just on R6. So it is linear with coordinates Q1, Q2, Q3, P1, P2, P3. And I have a constraint phi equal to third component of the momentum equal to 0. Then kind of if I follow the Dirac quantization, so I first kind of work with an auxiliary Hilbert space for the big unreduced system, which in this case, of course, would be square integral functions on R3 with respect to the trivial measure, and the wave function, a general element here, will just depend on 3 arguments. Now, the Dirac prescription says applying the quantum constraint, so the quantization of this classical constraint onto the wave function, which in this case is, of course, P3, which is the same as minus I h bar d by dq3 psi is equal to 0, has to be satisfied for all physical wave functions. And of course, then kind of trivially can read off that all physical wave functions will be just those that simply do not depend on the third argument. And you would say then, well, the physical Hilbert space is then the space of all square integral functions of R2 dqi. But then I also, you see, I already warned you, I mean, strictly speaking, of course, these are not, this is not a subspace, or rather there's the function, well, this is not a subspace of this one here, naturally, unless, I mean, you allow also non-square integrable functions here, because the ones that get projected out are those that are constant along Q3. Yes, and those, of course, in principle, then give you infinities in the dq3 integration direction. Okay, now, and I also pointed out to you that one very quickly also runs into other types of problems with this prescription, which one then has to take care of in some way, which is not always possible. So consistency, Dirac consistency, that must mean he pointed this out in the first place. I think that is exactly in these lecture notes. I recommend it to you, is that we must have that psi A hat, quantum commutator psi B hat on physical wave functions must vanish. And that was the quantum counterpart of saying the classical Poisson bracket of a pair of constraints has to vanish on the constrained surface. That was a classical consistency condition. But if you just have a generic quantization procedure, say for the Q's and the P's, and depending, of course, how complicated the functional dependence of these constraints is on the fundamental variables, you may run into problems, and it doesn't follow in any way that you reproduce the classical algebra in this sense, that you have a FABC hat. If these came from these are just kind of the straightforward quantizations of the classical phase space functions, phi C. Because in general, as I pointed out to you, because of operator ordering problems. So what is generally the case? I mean, if some or all of these kind of, for example, appear to the right of these constraints, then, well, of course, you can bring them to the canonical order, just a sec, So in general, of course, you can then, if some of this happened to be to the right of here, I can bring it into this form by commuting it once more, but then I'll pick up an additional term. So in general, what will happen is that phi hat A, phi hat B is equal to I H bar F A B C phi hat C plus some additional terms proportional to H bar squared because they involve one more quantum commutator and some array where at least some of these entries are non-vanishing. Yes?
So if you want this equation to be acting on some state, because as a quantum equation, this would be very strong, right? Because there, the quantum version was always constraining something that is acting on physical state.
Yeah, but that's
what you mean?
Well, classically, no, I think these two things for the simple case are equivalent. So you just need there to be no new constraints that arise when you take the commutator. And that you're only assured of on the state, say also physical wave functions, is this kind of appear to the right, because there's no reason whatsoever why these should annihilate, in general, the states. So this is, of course, exactly captured then in an additional term. And you see then on physical wave functions, requiring the vanishing, requiring this consistency condition to be fulfilled, gives then rise to an extra constraint. So if that is non-vanishing, this D. So you get extra conditions. D hat A B psi equal to 0. And in general, these will impose conditions, that have no counterpart in the classical theory. So they will constrain your degrees of freedom more than you intended originally, or was the case in the classical theory. So in that case, one says then that a classical symmetry that was kind of generated by the flow of these constraints is broken in the quantum theory because it's no longer present in that same form, or just not present, right? So in that case, kind of the gauge invariance, this one says, is broken at the quantum level. And one then speaks of an anomaly, or a gauge anomaly. So it simply just means, the classical algebra of constraints, which were symmetry generators because they correspond to a first-class set. This is my assumption here. They don't satisfy that same algebra quantum mechanically. So for example, if now you had, this could have been first-class constraints, but could be other symmetry generators. If their classical kind of well-defined, say, Lie algebra relation is no longer present, is broken in the quantum theory, it, for instance, could mean if they corresponded, say, to a global symmetry, that although they appeared to be kind of a symmetry and, say, a conserved current, classically, this is not so for the true theory, that is a quantum theory. Right? So this just happens. And of course then, you tend to have a problem. Your theory has a problem. Now, of course, we are interested in what all this means for gravity. So what does the Dirac quantization for gravity amount to? And are there any problems, or can I just push through this quantization program? So of course, the first difficulty is, of course, that I'm translating this now to a field theoretic context. So I have to be careful, of course, my operators, etc. It requires much more work that these things, to prove that things are well defined. However, what one does is usually one just proceeds in analogy, kind of with finite dimensions, and when one sees then of a formal quantization. That just means, well, if everything goes well, if you can make all these relations well defined, I'll comment on this more a little later, then things just might go through. But of course, there's absolutely no guarantee that this happens. So at this formal level, kind of you are thinking of a Hilbert space of wave functions that depend just on the configuration variables of the classical theory. That is, of course, the analog of the phi of x, right, in quantum mechanics, psi of x. So that's step number one. And then you just promote Poisson brackets to canonical commutators. So that would be to say, of course, I had written down the commutations, the Poisson relations for the Hij's and their canonical conjugates on the blackboard yesterday or the day before. And now I just imagine, I have a bunch of self-adjoint operators, obtained by hatting of these classical things. And so I hope these exist in some way. And if they do, I'd like them to satisfy these relations, which are just the quantum analogs of the classical relations. Delta IK, delta JL, plus delta IL, delta JK, delta 3 of X and Y. Well, of course, we are not finished, because then we had these constraints, the 4 quantum constraints, classical constraints, which you now want to quantize. So let me again collectively call them curly H mu, not to be confused with the symbol for Hilbert space I've used up there. So this consists of the H perp, the Hamiltonian constraint, and the 3 diffeomorphism constraints, Hi. And then, according to the Dirac quantization procedure, demand that these quantum constraints should vanish on physical wave functions. I mean, this should kind of project out some physical Hilbert space for me. And lastly, well, I mean, this physical Hilbert space should really be well defined. For this auxiliary Hilbert space, well, to what extent this is necessary is maybe debatable. But here, we really then want to find kind of a scalar product on the space of these physical wave functions. So to obtain some well-defined Hilbert space, H physical. So this is my kind of my naive quantization program. This is how I would want to proceed. I mean, in complete analogy with finite dimensional examples. There is a host of problems associated with this. If I really try to implement this, let me just mention a few of them and write some down. Well, first of all, that's already known kind of from in finite dimensions. If I have this type of kind of Heisenberg algebra relation, so I have an x x hat with p hat commutator is proportional to the unit, then if I impose kind of standard quantization, the nice thing is that this is essentially unique. But certainly classically, so if you finite dimension, it implies that both the spectrum of the quantum operator x hat and that of p hat is the entire real line. And certainly, in this case up here, if something similar happened, that would appear to be in conflict with my requirement that the determinant of h should be larger than 0. So it's not the case that all these arguments, are allowed to take values over the entire real line. And I would expect that the wave function should in some way also know about this. Okay, so it's not clear whether this type of fundamental commutation relations captures this correctly. Tendentially, not. You might say, well, maybe I can get away with this if I consider just certain compound objects built up of these fundamental variables. And that's in principle possible. Now, another thing which spells trouble is that what entered in this uniqueness in the Stone-von-Neumann theorem in finite dimensions is also the Hilbert space itself. And the Hilbert space was square integral function with respect to the Lebesgue measure. What I call the trivial measure, dqi. Now, such a Lebesgue measure does not exist naturally in infinite dimensions. So that raises the question: what is this? What is a good functional measure? And thirdly, of course, as you have already seen, in these constraints are rather complicated functions of the basic variables, and in particular, the Hamiltonian is a very complicated non-polynomial function of the classical phase space variables. And clearly, I'm going to meet even massive operator ordering problems, potentially, in quantizing this, even at this very naive level. So there are various problems that are potentially there, but they're not only potentially there. If one really tries to make sense of it, one sees that they are really there. Now, one kind of the obvious thing to try and do is now implement, as you would do in finite dimensions, this hij hat as a multiplication operator and the pi as a functional differential with respect to the hij's. If you do that, then one can say, okay, let me assume some operator ordering. So I'm just substituting in these dependencies, these quantizations, these kind of elementary operators, and a popular choice is have it ordered in such a way that all momenta appear to the right in the constraints. So that's one thing you can do. What this amounts to for the four quantum constraints is the following. Hi hat acting on a wave function that depends on the hij's is equal to minus 2 dj hi k minus I h bar, and now comes the differential operator. So that was exactly where I had a pi dependence, classically. That now becomes a partial functional differential on psi. And this is my kind of one of my Dirac conditions on the wave functions, on the physical wave functions. The Hamiltonian constraint, if I do the same thing, I end up with a formal kind of quantum operator minus, this is kappa squared, h bar squared, gij kl, and then a double derivative, because it came from a pi squared term, del by del hij, del h Okay, L minus square root of the determinant of H, kappa squared, three-dimensional curvature acting on size equal to 0. So you see, we've kind of formally adopted Schrödinger type quantization, where the momenta are represented by these partial derivatives, and we've, the choice is made that they appear to the right, the derivatives. Because here, of course, there is Hij dependence in these expressions on the left that multiply these differential operators. Okay, so a choice definitely has been made. And by deciding to represent these H's as multiplication operators, well, at least you can very easily write down these things. I mean, they just look like classical. This depended on the Hij's, for example. And of course, so does this and the partial, the covariant derivative here. Now, this second equation has its own name. It's called the Wheeler-DeWitt equation. Also sometimes abbreviated as WDW equation. It's of course a famous name, which you might have heard, even if you don't know too much about quantum gravity. Let's have a look about what these mean, these expressions, or what the geometric interpretation might mean. Well, as it turns out, whenever things are just linear in the momenta, and therefore kind of linear in these derivatives, I can just think of them as, well, vector field, very much in the same way as I did, in my baby example, where I set P3 equal to 0, and then had a kind of could think of the action of the associated quantum operator as acting on the argument on the domain of my wave functions, which there consisted just of the three directions in R3, and just moving along the gauge direction here. And a very similar interpretation is possible when one has constraints that are just linear in the momenta, and I've written them, I mean, the way I've written them here with the differential operator to the right. They also will act, you can think of them as acting kind of on the arguments of the wave function and just moving within that space, the Hij space, the superspace, moving you in the direction of three-dimensional spatial diffeomorphisms. Okay. So what I mean to imply by this is that these constraints, these three constraints, have an immediate and straightforward geometric interpretation. So they just move the argument or they act on the argument of the wave function, that's how you can think of them, as a three-dimensional diffeomorphism would, infinitesimal diffeomorphism would. Okay. And if we compute their algebra, they exactly reproduce the infinite dimensional Lie algebra of the three-dimensional diffeomorphisms. So that's fine. So they, on the face of it, it just means that the three-dimensional diffeomorphism symmetry is kind of exactly reproduced at this level in the quantum theory, and requiring things to be invariant means just has an immediate physical interpretation of saying, aha, these are just wave functions, kind of invariant under 3D diffeomorphisms. So they will depend on data that are kind of gauge orbits with respect to these diffeomorphisms. Okay. I'm not saying that it's very easily kind of implemented in practice necessarily, but it's kind of a straightforward mental image of, of what happens. So this is my comment concerning these Hi heads. So they generate spatial diffeomorphisms at the quantum level, and without any anomalies, at least at this very formal level I'm using here, and a wave function that is annihilated by those is one which depends kind of only on equivalence classes of Hij's. Yeah, so if this is a diffeomorphism invariant functional of Hij. So it doesn't depend on Hij, but only on the equivalence class with respect to this group action. So it's a functional on superspace. If by superspace I now understand the space of geometries where I have factored out by this gauge freedom. Now, let's come to this beast here. So the Wheeler-DeWitt equation. So this is what gives you all the trouble in the canonical quantum theory. So you can already see it's classically already a very involved object. It is more particularly it's quadratic in these functional derivatives, which also means so these are acting at the same point. So it's highly ill-defined. So this a priori doesn't make any specific sense before I have at least, say, regularized kind of the infinities that come from this double derivative at the same point. And the issues that have to do with operator ordering and things like, can I implement at the quantum level the full Dirac algebra in some way? Can I find a representation which achieves this? Is intimately tied to the regularization. Because, well, without the regularization, it's the question is totally ill-posed. So it's only well-posed if I regularize. And then, of course, the regularized operator will then have a certain commutation relation with itself and with its Hij's. And then I have to kind of study, and I have to be careful how I smear things out, that, whether I can reproduce in any sensible limit where I remove then these regulators. Say, for example, the Dirac algebra, which I would love to do in principle. Yes?
Why is it that the second derivative is very specific?
Oh, yeah, because they depend on the same. This is because of functional equation. I've now suppressed, of course, all the arguments.
Delta function or something.
Yes. So, yes. So simple smearing out will not do. So you have to regularize this. So that's my remark here. Anyway, this is, even in standard quantum field theory, the very same phenomenon would occur. So this must be regularized and potentially renormalized. And, well, just the point I also want to make here is that this cannot be separated from the factor ordering question. Now, if you kind of close your eyes to this and just formally kind of takes the commutator of these expressions, then unfortunately you don't reproduce the Dirac algebra, not even at any formal level. So if you just ignore the singularity issue, well, which I'm telling you shouldn't. People looked, when I became interested in quantum gravity, that's a long time ago, well, people just had been banging their heads against the wall, trying to make any sense out of this equation. And of course, what you have to do in the quantum theory also, well, this is, of course, it's straightforward even to write down this formal equation, but of course you have to solve it. And, well, no one has any idea how to go about solving this equation. So basically, one was very much stuck here. Things you can try, of course, I mean, people tried with factor orderings, but there is no factor ordering that even formally reproduces the Dirac algebra. Then you can try and go to a simpler context, and you can say, for example, people look at this problem in cosmology. That means you already classically throw out almost all degrees of freedom, because you say, oh, let me consider universes that are, homogeneous and isotropic. So that's what you typically do. It's a very successful approach to describe large-scale cosmology. To what extent it really makes a lot of sense in the quantum theory is yet another question. But one can try and do that, and then one meets the Wheeler-DeWitt equation in a much simpler context, like it looks like a quantum mechanical problem. But even there, in most instances, you have exactly factor ordering problems. I mean, you don't have the singularity problems that arise because we are talking about a field theory, but you have nasty problems that come, if you recall what I said at the very beginning of the lectures. Here we have function of configuration variables times a p-squared term. So you always have these factor ordering problems, and of course you can sometimes find factor orderings for which you then can solve, let's say, a cosmological approximation. What it all means is another question, but even in that simplified context, you are very often unable to deal with solving this equation at all. So it's a famous equation, but, well, what it has done for us so far is maybe, is subject to debate, I would say. So that was my first remark. My second remark, is that we simply don't know how to solve H perp hat psi equal to 0. Certainly not in this metric formulation. And what I start explaining to you a bit about today, so what gave new impetus to this canonical quantization program, 25 years or so ago, was the discovery that with a slightly different choice of basic variables, so not the Hij's and their conjugate momenta, but some kind of gauge theory-like variables, one can transform this equation into something simpler. And one has a reasonably nice way of treating rather explicitly these diffeomorphism constraints. And that is the framework of so-called loop quantum gravity. And I'll get to this in the course of my lecture. After having made some more remarks on this general Hamiltonian scheme, so also one question is, well, what on earth, I mean, what's the physical interpretation of this Wheeler-DeWitt equation? And already, of course, classically, we met this somewhat strange feature that, well, this looks very much like a Hamiltonian, but I require it to vanish classically. And that's, of course, a quantum analog of this statement. And if I think of a standard way of phrasing dynamics, of course, I'm thinking of something like if I have a Hamiltonian, I think of something like a Schrödinger equation, IH d by dt, time derivative of my wave function, is H hat. the Hamiltonian, in this case, of course, this would be the kind of the integrated 1/3 slices of t acting on psi of t. And recall, this was a linear combination with the n's and the ni's of these two sets of constraints. So this seems an equation, an obvious equation one would write down for the quantum theory in gravity in this canonical formalism with the Hamiltonian, with some kind of quantized Hamiltonian here on the right-hand side. But of course, by definition, this is just a linear combination of constraints. So on physical wave functions, this vanishes. So, well, this is 0. And then you look at the left-hand side and you think, oh, well, what does that mean? It means all wave functions are constant. I mean, nothing's happening. And people sometimes capture this by saying, well, time is frozen, right? Because apparently nothing seems to be happening. But obviously, to conclude that there wouldn't be any interesting evolution in the quantum theory is clearly a wrong conclusion. I mean, it can't be right, because of course, classically, although H is vanishing, of course, there is lots of non-trivial evolution. You know, we have classical solution with non-trivial time developments, and that clearly we expect also in the classical theory. So again, that raises that. Then one would conclude, oh yeah, but T meant something quite different in this theory than from what it usually means. So, and one of many ways of making sense, nevertheless, out of this formalism is to interpret, to look for another notion of time within this physical system, which is extracted as, well, will depend on the HIJs and the pi ijs in some way, but will be physically motivated. And then kind of rewrite even the quantum mechanical expressions as functions of this kind of physical time. And as soon as you do that, then you're back to a more standard formalism where you have a notion of time and you will have a conjugate, a quantity which you might want to call a real Hamiltonian or an energy. And then you're more in the realm of, yeah, familiar descriptions. Whether that's the right thing to do is yet another, is yet another question. Or there is a whole, I mean, hundreds and hundreds and hundreds of pages have been written about the problem of time in quantum gravity. And I'm not even trying to convey, the depth of the arguments to you in this lecture, because also I simply don't have the time to do this. I wanted to give you, yes, just one of the references is by, so this is on the archive, is by Isham, kind of a classic paper, QC 921001. One is called Canonical Quantum Gravity and the Problem of Time, and it has about 120 pages or so. And there are more extensive other papers and books, some of them with Isham as a co-author. So he was really authority on these time questions, and still is, where one discusses all possible alternatives to extract the time, what it means, is it there, is it not there. So I recommend that if you're interested in the details. Of course, it somewhat hampered these discussions by the fact that we have no real, complete quantizations available. If we had lots of different quantizations, and the, quantization A treats time in a certain way, quantization B treats time in another way, and then you would get results from those, and then you could start comparing the results. Well, then life would maybe be easier to decide what's a reasonable strategy. But we don't really have, we're not in the state for the most part to do this. Okay, now here, as I mentioned briefly, one appeared to be a little bit stuck with this kind of standard canonical formulation in terms of these metric variables, geometric variables, as they're sometimes called. And here now came a bunch a new idea, a fresh idea, how you might reformulate the classical theory totally equivalently in terms of a bunch of different variables, which would then suggest different ways of going about the quantization and the canonical quantization in particular. And these new variables are called connection variables. And, well, the key person to put them on the map was Ashtekar. This was in 1986. And this led then to what is now known as loop, or has been known for quite some time, as loop quantum gravity. I understand that there will be a set of lectures later on in the Psi courses given by Rovelli about quantum gravity. And I'm sure he will also tell you many more details about loop quantum gravity and what has become of it. So what I'll do here is I'll be very brief, give you some of the key ideas of what one does and how it differs from what one did before and why this enabled one to go somewhat further in the quantization. But I'll by no means be covering this in any great depth again. Okay, now, what is the key idea? The key idea, you have a classical reformulation, as I said, which is totally equivalent. I mean, describes the same Einstein equations, the same solutions. And it's given to us in terms of a so-called first-order formalism. Let me start a new half blackboard here. So this is a classically equivalent so-called first-order formulation. I'll explain in a second what this is, of general relativity. So what are the variables that appear here in terms of an orthonormal frame, so in each space-time point, can also call it a tetrad or a vierbein field. Orthonormal frame field, and the notation for those is little e, space-time index mu, internal index capital A. So that refers to the kind of the frame in each space-time point. So I have kind of, an internal space. The label capital A runs, of course, also from 0 to 3. And this is an internal, and mu, I should also, mu, of course, likewise. And the A is an internal SO algebra SO31 index. So that means you think of a kind of a Minkowski vector space with Minkowski signature attached to each point of your base manifold. How are they related? How is this field related to the G mu nu, whose interpretation we are familiar with? It is a kind of, as one says, the square root of the metric. So G mu nu is equal to eta AB. So this is a Minkowski metric on this internal space, epsilon mu A, epsilon mu B. So this is the internal Minkowski metric. And what else do we have? And the spin connections of the frame field. Whoops, so this is an aside. And a spin connection. A spin connection. Omega mu A B of X. I don't know whether you've met the spin connection in your GR lectures. I don't. Yes, that's what I meant. Okay, good. Well, spin is closely related to the Levi-Civita connection, right? And this is, of course, what I need in parallel transporting not just vectors but also spinors, and is an object that contains first derivatives of a metric. So you see, and whereas E is a function of the metric, right? So what one means by a first order formalism is one writes down an action, a Lagrangian, which depends on, well, these tetrad fields, plus connections regarded to start with as independent variables, right? So no explicit then kind of second order derivative terms appear at this stage. But then when you start then writing down the equations of motion, right, you of course can then substitute the solutions of one into the other and rederive the standard second order equations of motion. But doing it this way is an example of what's known as a first order formalism. Now, of course, not only that, what comes with this here is new degrees of freedom, right? Because there are a priori more degrees of freedom contained in these tetrad fields than there are in the metric, because they carry an additional index. Yes. With this additional index, but of course, you see, because it appears in this way here in the metric, applying an SO3 rotation on these dry binds internally doesn't change the metric. So you're picking up new degrees of freedom, but these are gauge immediately. But of course, we will carry around this newly acquired gauge freedom plus, this new internal degrees of freedom with us in the formalism. So they will appear now in the classical formulation and will lead to additional first-class constraints, okay, that are associated with these internal rotations once we get to a 3+1 decomposition. So this is at the level of the, these are the variables that are relevant at the level of the Lagrangian. And what one then does, actually, one doesn't work with these omegas, but with a closely related but derived new connection form. And again, I'm not going to present you with any of the details here. After having done this, one then performs a 3+1 decomposition. So totally analogously to what we did in terms of the metric variables. And one also performs a partial gauge fixing on these internal rotations. So one breaks it down by making a specific gauge choice. One breaks down the SO31 to an SO3. So that's all that remains of this new internal gauge degrees of freedom. And that's kind of crucial to make the formalism work and to get to the functional form, which I'll be presenting to you in a second. So composition and a partial gauge fixing. SO3 1 to SO3. And then the marvelous thing is that the resulting variables one obtains in the Hamiltonian formulation, they look like Young-Mills variables with internal gauge group SO3. So they are just kind of a gauge potential and a conjugate momentum. Looks like exactly, I mean, the fundamental variables as they look when you do a Hamiltonian analysis of, say, Young-Mills theory, yeah? But with this somewhat unusual gauge group SO3. Of course, we're used to that for the SUN. What appears in gauge theory applications is usually as SUN. So one ends up with Young-Mills like conjugate variable pairs And let me straight away write down kind of both the variables and their canonical Poisson bracket relation. So one has a kind of a gauge potential depending on x. So we are now thinking of, spatial slices. So these live now on spatial slices. And we have conjugate E variables. And they commute with some coupling constant in front to give delta functions, Kronecker with respect to the index labels, a delta AB and a delta IJ, and a Dirac delta function with respect to the spatial arguments. And of course, that it's an equal time Poisson bracket. And this beta here is a so-called Barbero-Imerzi parameter. Imerzi parameter. So that appears in this formulation. It's a priori, it's just it's a complex it's a complex non-vanishing number. So here ij, just to fix my notation, equal 1 to 3 are spatial indices. And A and B, also running from 1 to 3, is an SO3 index. Now the AIAs, so I could call the space of all of those a big curly A. These are SO3 connections. Or you could call them gauge potentials. So that of course refers to the way they will transform under coordinate transformations. And the A, that is the internal index. And if I were talking about Young-Mills, that would mean, well, the A's take their values in an SUN algebra, and here in our case they will now take values in an SO3 algebra. The E's, E, B, J, have a transparent interpretation up to a determinantal factor, square root of h, which if you want, you can now express, of course, as a function of the little e's, the tetras or the spatial components, times E, B, J. Okay, so these are essentially triads or dry-bind variables, these things, up to this weight factor. Yeah. So this is also called a densitized triad. Beautiful piece of jargon. Okay, now, this is not a Young-Mills phase space, because there is an associated curvature with this such an A. So here we have an associated curvature. Fij A, and this is exactly the formula you're used to from gauge field theory, apart from some dimensionful coupling constants floating around. So this is G Newton. So you get a kind of anti-symmetrized first order derivative term, del I Aj minus del J Ai, plus a term that's quadratic in the A's. Epsilon ABC. These are, of course, the structure constants of SO3. A, B, I, A, J, C. Now, what interests us is to start with classically what's a constraint structure, and then how can we quantize it? And the issue of how can we quantize it, one would then try and make crucial use of the fact that one is working with Young-Mills variables, and try to import some concepts that are known to work well in this case. Just as a very brief last remark, you can see that this throws a quite different light on things, because here we are in a formulation where what came from the metric variables, that is the E essentially, that was the square root of the metric, appears naturally as conjugate momenta, and therefore will naturally be represented as derivative operators in the quantum theory. That is, of course, exactly the opposite of what happened in the metric formulation, where the metric was represented as a multiplication operator. So you can already anticipate that there might be certainly some qualitative changes in the types of equations you're writing down there. So there is a chance that maybe everything will look nice and different, and you can progress further than you could in this old formalism. And to what extent that hope is justified, we'll talk about next week. Thank you.